At a very basic level, the internet is this thing that lets us send data from one device to another. In this video, we'll outline what actually happens when a client like you sends some information to a server, such as the YouTube servers. We'll start at your web browser, head over to the YouTube servers, and come all the way back. So we'll be covering a lot of ground in this video, and it might be difficult to comprehend if your understanding of the internet is very limited. But in particular, I'm going to try to emphasize the state of the message at each step of the way. To understand the idea of your message changing states, imagine sending a letter to a friend. That letter will be in different forms throughout its journey, from a blank piece of paper to a written letter with an envelope. In the networking world, these different forms are different layers of the data transfer process. Our message will actually be layered and unlayered with various protocols as the journey unfolds. Each of these protocols are used by different services or layers at different parts of the journey. Hypothetically, the sender could just abandon these protocols, but then the devices along the network wouldn't be able to understand the message, and the message might as well be useless. Next, we can go ahead and break down this data transfer process into its parts. So we start off with the formation of the request by the client. Then we send the request over the internet. Next, the request is processed by the server. Next, the server will go ahead and form a response. And finally, the server will send the response over the internet, and the client will process that response. Each of these steps will be labeled at the top throughout this video, and they make up what is known as the HTTP request response cycle, the basis of how we transfer internet over the web. But before we get into the journey, let's discuss the parts of the internet. At one end, we have the local area network, which is basically your home and its devices that are connected to a router. The device that is sending the request is the client. On this client, there is a specific service or process that will make the request and receive the response. In this instance, we're using a web browser, Google Chrome. Next, the switch, router, and modem together help connect our device to our local area network, which is connected to the internet through an ISP, or Internet Service Provider. On the other end, we have a server owned by YouTube. Here, the term server is referring to a singular machine that we are trying to connect to. Note that the server will also have some service or process running on it that will handle our request. The internet refers to the infrastructure used to actually transport our message across large distances. To simplify things, the internet consists of a series of routers that will route our message to the server. We'll hold off on discussing DNS, or the domain name system, for now, so we'll go ahead and initiate an HTTP request response cycle to start up our journey. First, we need to create the message that we want to send. We could send an email, a file, or something else, but in this case we want to send an HTTP request because we're trying to receive back an HTTP response in the form of a web page. It's important to note that all an HTTP request is just a string of text that's formatted in some special way, and so are HTTP responses. The reason web pages appear to look like something and not just strings is because of all the work the browser does to display it, but more on that later. Now, we could create this request string ourselves manually, but we'll go ahead and use a browser to make the job easier. In our browser, we simply need to supply a valid URL to make a request, and the browser will take our URL and dissect the scheme, host, path, port, and query parameters from it to create an HTTP GET request. In this instance, we're making a GET request to the host www.youtube.com, supplying a path of /results and a query parameter of search_query, which is set to the value cat. The URL also determines the destination port of our request, which identifies the particular service on the server we want to direct to. Since we didn't explicitly identify a port in the URL, it's assumed to be port 80, which is basically the default port for HTTP requests. Now, as you can see, the method path and HTTP version are included in the first line of our request, the request line. The request might also contain some headers and body. But what about our host and port? They were never included in our HTTP request, so why is this? Well, let's take a moment to think about the purpose of the host and port. The host, such as www.youtube.com, is used to determine the destination to which we want to send our request. And the destination port determines the service on that destination host that we want to send our request to. But the HTTP request itself doesn't really need to be concerned with these things. Those are only important once we get to the layers that are involved with actually transporting the message around. So what do we do with these things? Well, to make things simple, we'll just hold on to the port for later. But the host, www.youtube.com, is pretty useless as it is. It's just a domain. In order for us to travel anywhere on the internet, we need a destination IP address, not just a domain, since IP addresses actually identify devices on the internet. So what actually happens is that the supplied host will be converted to an IP address using the thing we mentioned earlier called DNS, or the domain name server or domain name system. The host www.youtube.com must be matched with a corresponding IP address. So first, the local DNS cache is checked to see if there's a match, and if not, the DNS servers are searched. Let's assume that's the case here. And the DNS servers are essentially a database distributed across multiple servers. Now, once an IP address is found, it'll be sent back to the client in the DNS response, and we'll hold on to this for later as well. So far, the browser has an HTTP request, but we are far from ready to send it over the network. Right now, our request, you can kind of think of it as just a piece of paper with a few words on it. We need to go ahead and buff up our message with a few more protocols, and we achieve this by passing it through so-called layers. A layer refers to a group of protocols that achieve a particular function, such as directing data to a particular application or routing data over the internet. When we pass through a layer, the state of our message changes. The state of a message at a given layer is called the protocol data unit, or PDU. Right now, our PDU is an HTTP request, but for lower level layers, we have different names for different PDUs. So we've done everything we need to do at the application level, but now we need to prepare our message for sending. At the next layer, called the transport layer, the TCP and UDP protocols are the two predominant protocols you'll see. For requests using HTTP2 and below, TCP is used to perform the transport layer functionality, so we'll assume we're using TCP here. Let's discuss two super key networking concepts, ports and sockets. Each networked process currently running on any machine is assigned a port number. We have a Chrome tab running on port 49280 and another Chrome tab running on 51032. A socket object can be created for each port to allow the device to send and receive messages from and to that port. Conceptually, this socket can be thought of as the endpoint for receiving and sending messages. Any messages sent from our first Chrome tab will be sent from this socket, and the response being sent to our first Chrome tab could be sent to this socket. The nice thing about the transport layer, and ports and sockets specifically, is that they allow for something called multiplexing, which is sending signals from different applications over the same singular channel on our device. Say we have a second browser tab open, which means a new process and a new port. Sockets allow us to redirect messages from these two separate Chrome tabs, or even other separate networked applications entirely, to the same singular channel on our device, and this is known as multiplexing, and it makes our job so much easier when we get to the lower level layers. We also probably don't want to send all the data in the request as one singular unit, because if it has a lot of data, it could slow down and congest the network at certain points. This is where the transport layer comes in, to break up our request into smaller segments that can be individually sent over the network. TCP will perform this segmentation process of dividing the application level data into chunks, each of which becomes the data payload for TCP segments. Besides the payload, each segment has headers for the source port and destination ports, plus a whole lot of other information. In particular, TCP has built-in measures to ensure reliable transport. For example, if a segment is lost on the network, TCP handles retransmission with the sequence number and acknowledgement number headers. TCP also ensures in-order delivery by assigning each segment a sequence number. TCP even provides some data integrity checking with the checksum header. Finally, TCP can handle flow control and network congestion issues by modulating the window size, which is another header. Now, I won't get into how TCP's reliability services themselves work, but just know that these headers are there for reliability purposes. So we've broken up the message into TCP segments and labeled them with headers. We have the destination port number, but what about that IP address still hanging around? We've addressed our message to the service it needs to be sent to, but we haven't addressed the server itself. This is where the network layer comes in, and this layer is really the backbone of the internet. It encapsulates each TCP segment with the IP protocol, which contains the source and destination IP addresses. The destination IP address is like a mailing address used to locate our destination on the vast internet. The source IP is sort of like a return address, and as you could probably guess, it's included so that the server knows who to send the response back to. The great thing about IP addresses is that they are dynamic. A device is dynamically configured with an IP address when it is included as part of a network, and this makes it possible to locate the device on the internet, but we'll discuss this a bit more in depth later. The network layer also provides, like the previous layer, a checksum header for error detection, and it also has a time to live header, which specifies the number of hops the packet can make on the network before it is dropped. This just helps to limit network congestion. We'll see this layer really come into use when we get to the internet section. At this point, it might feel like we're ready to send off what is now an IP packet, but we're still missing something. The destination IP address tells us where our destination is, but it doesn't tell us where the very next node is or the next router or computer that we need to send our packet to. It might be obvious to us what the next device is, but we're dealing with computers here, and they must specifically be told what the next device to send to is. The data link layer does this by encapsulating the packet using yet another type of address, a MAC address or Media Access Control address. The two protocols primarily used at this layer are the Ethernet protocol for wired connections and the 802.11 protocol for wireless connections, but we'll use Ethernet here. The source MAC address is the hard-coded address for our device, etched into our network identification card, or NIC. The destination MAC address is for the next node in our journey, which in this case is the router, so we'll include our router's MAC address. Don't worry too much about the thing next to it called the switch. We'll discuss that a bit later. You might be wondering how our device discovered the MAC address of the router to send to in the first place. Well, basically, our device would have discovered the router's MAC address at some point by sending some small packets of data back and forth. We won't get into that too much in this video, but we will discuss it a little bit more later. Since the Ethernet and 802.11 frames are closely related to the actual physical transmission of data, these protocols actually indicate how long the sender should wait between sending each consecutive frame, say 9.6 microseconds, for example. This gives the receiving device some time to prepare for each consecutive frame. Additionally, this frame also includes the length of the data payload so that the receiver knows when the data is finished when it's processing it. And finally, our Ethernet frame has a checksum footer for some more basic error detection, and this is called the frame check sequence. Now, things like the interframe gap or length or MAC addresses are the sort of things that we don't really think about when sending data as a human, but the receiving computer, we have to remember, doesn't have a human intuition. It needs exact instructions and information to be able to process the frame in a way that makes sense. Now, we're finally ready to send off our frame to the next node in the network. But before we do that, let's briefly discuss the actual physical representation of the data we're sending. After all, we are just sending the data over some physical system, whether that be cables or through the sky. So a physical thing must pass through that system. Let's discuss that physical thing. There are three main ways data is represented when it travels over the internet: light, using fiber optics cables, electricity, or radio waves. The easiest way to represent data using these mediums is with ones and zeros or bits, because we could turn light or electricity on or off. Radio waves can use different frequencies to represent on or off. So basically, our frame will be represented with bits when it travels over the internet, but the particular medium for that representation might vary. For most of the journey, though, it will probably be light via fiber optics cables. Now, we essentially just have a bunch of ones and zeros represented by flashes of light. But these ones and zeros are structured in a way that can be interpreted by the receiving devices, all thanks to the protocols that we discussed from earlier.